Okay, so I start now. Fine. And so first, what I will talk about, and no, what we usually talking or deal with concentrate about several things, and at least maybe part or one half of such things is what is some vertex operator algebras, which are related with many things. And then we have also quantum groups. And in principle, many other things. But if we are comparing these two objects, then it is also what is calling the screening operators, and maybe corresponding local system or D models in configuration spaces or other spaces. Anyway, so it is what I am talking is just keywords, but to talk about something, I need some concrete goal where to move, and because this lecture they have to be understandable, at least partly, then I want to choose as a goal. If I can explain it fast, it will be nice, but how fast I do not know. The relationship with all this business with integrable systems of KdV type. There are many of them, and no, formally this object is not directly part of this, but first of all, from many different sides, it is part of this. And about the integral system of KdV types, we have some problem, and this problem actually is the following, that I'll explain details later, but if you are talking just about this, no, surely a little bit non-precise, the problem is following. Here, you have circle and as a manifold. And on this manifold, you have a data of Schrödinger operators. Q is all this living on a circle. Actually, Q is quadratic differential, but it is right now, it is not important. Anyway, the structure which we have here usually is following, that this is some infinite dimensional manifold. Point of this manifold just such kind of operators, and this Q. And on this manifold, we have Poisson structure. Actually, several Poisson structures, but one of them is calling the second Poisson structure of KdV system, and with this structure, this object is just dual space to Virasoro algebra. Anyway, right now it's important to understand that this is some kind of infinite dimensional manifold which we can describe as a space of operators or a space of functions like this. We have here the Poisson structure, and then it is a way which I describe later to write down on this space of differential operator the sequence of functions. First function is the integral of q, second function of integral of q squared, third integral of q cubed plus some additional term. And such kind of functions, they commute with respect to this Poisson structure. And this is Hamiltonian description of system of k-derivative types in the following sense, that no, we have some Poisson structure, we have some functions there, and each functions give me some flow, and this flow which corresponds to this is simple. It is just rotation on a circle when q, x, each is moving by this flow going to q, x plus t on this circle. It is just this. But if you consider this, it will be more interesting things, and so it gives us some non-trivial vector fields on this infinite dimensional manifold. And this is the corresponding flow or corresponding differential equation where you describe the moving of such kind of differential operator. This is just KdV. Anyway, it is usual story in integrable system that you have some data which can be differential operator of second order, third order, or so on. You have no, it's not always, but in many cases, on a space of such data, we have Poisson structure, and we have also some special functions which are in such business usually given by integral of differential polynomials here like q. For these two we have no derivatives, but here we have. Yes, and we have infinitely many of them, and this is such kind of story usually calling integrable system of k-derivative type, and there are many of them. And people studied many years, but the question which we have here, surely we have many questions, but because such kind of system appear how? We have some manifold, which is in this case differential operator of second order. We have sequence of functions, h1, h2, h3, and so on, and they are no, in this case they have some special form, but in principle they can look differently. But the important things that with respect to this Poisson structure, they are in involution. Yes, and so we are living in the world of this integrable system. Then the question is of quantization. Quantization, it means that no, because we have Poisson structure on this manifold, and we know that if we have Poisson manifold, in principle, it is some quantization. So from this, we can produce some family of algebras. H is a parameter of quantization, and if H goes to 0, we recover the M with corresponding Poisson structure. And here we have H1, H2, H3, and so on. Then, and if we have such kind of quantization and no, about quantization, in principle we believe that it is canonical one, but believe or not, but in all examples, if we have usually only one, and we want to find here the system of elements, say 1 cup, H2 cup, and so on, which are living here, and commute. If you do it, you get quantization. So again, and if you achieve this, after that you can consider representation and play with the eigenvectors and so on, but at least you have to start with this. And maybe I'll try to explain several things if how much, it's not clear, but I will try. Anyway, maybe about 25 or maybe more years ago, we had with Edith Frankel some article where we did this. In this special case, we explain how to quantize in this example and in some maybe a little bit more complicated example, we explain how to do it. And so it means the following, that in this special case, I said that this Poisson structure is a dual space to Virasoro algebra, and so it means at least here quantization is natural, and the algebra where we want to find the commutative operator is just universal enveloping of Virasoro. So quantization of this is Virasoro algebra, where we have standard basis Li and central element, and Li Lj is j minus I Li plus j plus zero, and C is central element, and this is quantization in the following sense, that you can ask me, so I think everybody knows what is this, but quantization, it means that if we take just universal enveloping of like this, and if send C to infinity, then in the limit, when C go to infinity, you look to the limit of this algebra, and if you do it properly, then corresponding algebra become commutative, and you recover Poisson structure, and this Poisson structure will be just this. Anyway, from this point of view, C is central charge. So it is, in Virasoro, it is usually central element, but we can put this by this number. This number is central charge, and if we fix this number, we have a family of algebras which we can denote by Virasoro, and we can put this parameter C here, and this parameter has to go to infinity. This is what I said, or at least had in mind. Well, and the problem here is following, that if you are talking about Hamiltonian like this, then after quantization, it gives us definitely L0. It is very clear. If you are talking about integral of Q square, then it gives you the object of some Li, L minus I belong to Z, and usually you have to put here two dots. Yes, in physical notation, this is something like Tz, integral of this, and this is integral of Tz square, like this. And then next it will be t cube z 2 dots plus something like that, and next will be t fourths plus additional terms and so on. And the problem is that inside universal enveloping of this, or better to say in some completion, or in the corresponding vertex operator algebra, how do you can see this? You have a sequence of such elements, yes, and they are corresponding to these Hamiltonians. And what we did with Eddie Frankel many years ago, it was some machine which actually use these parts, this, and this, and we can derive from this the existence of such kind of integrable system. Yes, and so this is the problem. I want to explain how we did it and what was the logic, what the point of view, and so on. No, I cannot start with this because lecture has to be at least relatively elementary, so it is impossible. But as in introduction, let me just add a few words about some ideas that just a few words about what was the idea. The idea actually was the following, that here, in this case, we have some relationship of vertex operator algebra and quantum groups. No, Thomas gave lectures about this subject, and he explained something, but at least there are many relationships of this, and category of representation is connected, and also some other things are connected, and surely I cannot avoid later to explain something about this connection, but at least what I want to say that here, what quantum group can be here? You can take some UQ-SL2, and it is some machine which relate to with UQ-SL2 vertex operator algebra. No, in principle, there are many vertex operator algebra which are related with SL2, and Virasora is one example of this. And we can take, put on this place some other, say, group G, and can ask what we have here. And what we have here, again, they can be many vertex operator algebra, and most popular example is W-algebra, which connected with corresponding quantum group. And so it is very important from the theory of this to know that this quantum group is hidden somewhere. And actually, opposite is also important. To know if you want to study this, sometimes it is good to know and to have information in this side. Anyway, it's a standard story about W-algebras and quantum groups and so on, and people, and I'm one of such people, are saying that these quantum groups related with screening operators and so on, and blah, 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 and it is standard things. But surely after that, No, if suppose you know all this, then it can be a question that suppose on this part here, if you are talking about W algebra, corresponding Lie algebra on this side is finite dimensional. And structure, what is going on in finite dimensional quantum group, is something that's similar. You can play with usual quantum group, you can play with super version of quantum group, you can do something like this, and it is working. But in principle, here in this quantum group side, we have Kac-Moody algebras, quantum algebra. So in principle, following Katz and other people, we can take any Cartan matrix and or better in quantum group language, the permutation matrices. Right now, suppose it will be some Cartan, and we can construct corresponding quantum group. So this usual algebra and corresponding quantum group we can. And the question is what we have here. And do we have here something if we are working with more complicated and more generic things? And no, I think, no, my own point of view that in principle, if even A is generic, you can find something on this side. But you cannot it cannot be vertex operator algebra at all. It is not possible. It can be something different, and or it may be vertex operator algebra in some DG sense and so on, but I think yes, but it is not known till now. But if you are going this, you can make at least first step from finite dimensional to how people are going. So suppose G corresponding to affine Cartan matrix. Or it means, suppose that here you have UQ as to head, for example. So what we have here? Yes, and if you try to determine, just to repeat the way which I do not mention, but believe me that it is in principle, it is some way to go from this to this, you get something. This something does not have Virasoro inside, so therefore it cannot be vertex operator algebra. But again, even in this case, it is not known how to determine this object properly, but at least if you naively do the same story, you get some algebra which is not vertex operator algebra, but at least it is something. For example, if the machine, which I explain later, is working by the following way. We start with this, and as a result, we get some subalgebra inside universal algebra of Virasoro. And this algebra will be precisely what I explained to you. So it will not be vertex operator algebra, but it will be algebra which contain integral of t, integral of t squared, and so on. So in some sense, such kind of ideology, it says that this commutative algebra corresponding to affine quantum group by the same way as Virasoro itself corresponding to this. And no, and you will see how it is working, but just the end of this introduction thinks that No, Virasora is object which is which has many structures. It is vertex operator, defined vertex operator algebra, conformal field theory, and has complicated representation theory and so on. And if you consider this, it is just commutative algebra and nothing more. So it means that it more or less means that what you have here is a part of some bigger structure. But this structure is not known, but at least this, at least with this we can find. So, no, again, the logic of this old work with Edith Frankel was just this. So we tried to apply this to affine quantum group, and as a result, at least can see the existence of such things. And so this is what I want to explain, and that at least, as I said, all this and some other technical tools will be highly involved in this business, but now let me try to explain something, but I want to start with much simpler things about integrable systems. Well, integrable system which we are talking about now is what? That the question which I said that, well, we have Virasora algebra, or we have universal enveloping of SL2 hat, or we have more complicated vertex operator algebra, and inside this vertex operator algebra, we want to find out the commutative subalgebra, which is rather big, and no, the problem which I'm talking again is following, that if we have some vertex operator algebra, in a vertex operator algebra we have some collection of fields, OZ, or is local fields which is descendant of vacuums. So it is local field which is corresponding to vacuum representation. If we are talking about vertex operator algebra, we have vacuum representation, and there are many vectors there. And to each vector, I can correspond to corresponding some operator. Operator, it is element of some algebra, actually. At least we can think about him like this. And for example, in Virasora case, vacuum representation is looking like this: E, then L minus 2E, then L minus 3E, and then L minus 2 square, and so on. And to each vector is corresponding something from the algebra. To this vector is corresponding TZ. To this vector corresponding what is people calling like this. To this vector is corresponding to T square Z, 2 dots, and so on. Anyway, to each vector, it is we correspond some operator, and problem is again at least some possible way to formulate the problem. I want to find out the sequence of vector in vacuum representation O1, O2, O3, and so on, such that integral of O1z, integral of O2z, and so on, and or it means that there are currents and there are zero Fourier components. And so what we want such sequence, such say integrals of zero Fourier components commute. Yes. And from this point of view, we can formulate such kind of problem for any vertex operator algebra. And I want to say that in many cases it is possible to find them, and maybe in the very end I formulate what is known about some generic point of view. Actually, we have not generic theorem, but it is known where such things are possible to do. Yes, and but now let me say some introductory part of this. We are talking about rather complicated algebra, like vertex operator algebra, and want to find out commutative things there. But why not to take finite dimensional G and ask what people know about commutative algebra here. Surely they know much more, and there are several constructions here. Yes, and if we understand such integrable system here, that one way of thinking about this, I want to know about commutative algebras here, and then we will, if we will have some information, then we can make up affinizations. So then I can go to this, for example, it will be vertex operator algebra, and then we want to go from this to this. And again, like in all such kind of stories, this is vertex operator algebra, this object is living in the top of this, and if we have something here, I want to extend it to all vertex operator algebra, and this can be our problem. Then let me say, I hope not very long, but at least I need something from this to say about what is going on in this case. Without this, I think the vertex operator part is non-understandable. Well, then the most old and popular way is what is calling the shift of argument. No, it is good to explain something about this, because even the baby version of screenings we can see here. Now, what is this? We have shift of our argument business. G is now finite dimensional. Lie algebra can be superalgebra also. Then, first of all, what is this? We have G star, and we have function on this star. Maybe it will be like this. Yes, and on G star we have Kirillov constant Poisson structure. Yes, and if, what kind of functions it can be equations, suppose polynomials, then quantization of C, it gives us universal enveloping of G. And now classical story about integrable system, very, very classical, maybe 40 or 50 years, now living here. And the statement here is following. We can take and fix some element A from G star. Yes, and then this element A from G star is fixed, and suppose we have some function f from C G star. Yes, and we can denote by ft the function which is shifting by a times t, so ft of some x element from here is equal ft x plus ta. Yes, and the very, 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 very old statement is a very old theorem. So old that I don't know who first formulated and proved, but theorem may be constant. Theorem says the following. Suppose K1 and K2 are central functions on G star. Yes, and no, because they're central functions, they're central of the Poisson structure, so they commute with themselves and with all other elements here. Yes, but the fact which is interesting for us is what? That we can write K1 T1 shift by T1 this, and take K2 and shift it by T2, and then calculate the bracket. And this bracket will be 0 for any T1 and T2. This is standard theorem. No, I think that it is most people here know how to prove it, and first of all, it gives us the integrable system. So we have many, many functions which are commute. Yes, and no, I can prove it now, but maybe it is not good to do, and because I need some exercises for students, the students, if they know it's fine, they can explain me how to do it. If not, they can find place to read it and then explain it. Well, first exercise for student, just to find and to explain me the proof of this fact. Yes, and no, the proof is very nice and easy, and no, maybe I only want to say that surely in a case if G is, say, G_ln, then central are given by the functions trace of element from this power m, and then we are shifting this by a. So it means that we are considering element from this x plus ta, and then taking maybe it is the same as taking determinant of this, or characteristic from this point of view, something like characteristic polynomial of this. And it depending in T, and so we can get many commuting elements. Yes, and okay, so no, this is fine, and no, an integrable system which starting with quantization of Euler system on something like this, starting from the application of this for small gln, and so it was this. Now let us discuss the problem of quantization. So how it is going on? No, first of all, what we have in so this construction is very generic, but suppose we are talking in a case where the algebra G is semi-simple. Yes, and then we have space of function on G star. Yes, and if we have central element Z, no, in my notation K, here, then I can take KT so and consider the first derivative. No, KT is, it is shifting, so it was x plus TA. It is, but I want to consider what is happening if t is 0. It is surely our k, but I can take this function and consider the first derivative in t. So it is possible to denote it by this way, and it is first derivative of k. Yes, and then what we can do? We can consider all possible, I can fix central element and k, and consider all derivative, dk over dA. Yes, and so I have a collection of polynomials which labeled by A. And A is the element of G or G star. In this case, this is the same. So such kind of thing, or such kind of thing, give me a map from G or G star, maybe G better, to a function on G star. And this is gomomorphism with respect to a joint action. And yes, and the theorem about also constant is the following. So if we want to describe in a case of semi-simple G, all embedding of G to symmetric functions on G star. So how to do it? Actually, by this way. More precisely, constant, he formulated the following, he proved the following theorem, surely in much bigger generality. But in this case, he claims the following. No, we have center. We can put center in, for semi-simple Lie algebras polynomials in some generators. It is K1, K2, K3, and so on, maybe some KL. Yes. And each Ki gives me, by this way, the embedding of G into the space of function of G star. Yes, then, and we get the collection of embeddings as many keys we have. And surely we can take such embedding and product this to any central element. As a result, we describe all embeddings of G. And now, why I'm talking about this? No, this is because our integrable system is what? I'm taking central element and move it in direction of A. Yes, and there it gives me many, many elements, but if I restrict myself only by first derivative, then the corresponding elements are the following. I have functions on G star. Yes, and I take embedding from G to a function. It has to be embedding with respect to a joint action here. And we have some collection of embeddings. And then I can take A is some vector of G. And because I fix this and vary the embedding, so I have many elements from here. And from this shifting of arguments things, it is at least such kind of function on G star commute. And at least this is good for quantization. No, about quantization, we can say the following. Quantization now, we are talking about universal enveloping of G. And first of all, we know that if you are talking about universal enveloping as G model with respect to this adjoint action, that in this case it will be the same as this. And so we can just ask that we can consider just embeddings of G inside universal enveloping of G. Yes, and in principle we can study all embeddings of such sort. And no, in some sense we can describe them, no, quite classically we can describe them explicitly, but in the case of universal enveloping, maybe not so explicitly, but at least we have some number of these embeddings. And now it is possible to formulate still a rather simple theorem. Is following. Well, you consider such things. And suppose we have one embedding G into UG, we can just fix it. And by the way, it can be trivial embedding, where we can go just to G itself, or more complicated embeddings. So it can go just to linear part, to quadratic part, to cubic part, where each part which G want. But anyway, we can fix one. I can fix some other embedding too. And I can consider any element A from G. And so by first embeddings, this goes to element A. Let us denote it by A1. So this is image of A with respect to this embedding. And here we have other embedding. And again, A goes to somewhere, to A2. And just a theorem from semi-simple algebra business saying us that A1 bracket A2 is 0.
Excuse me, can I ask a question?
Yes.
So what kind of embedding you consider?
What?
What kind of embeddings you consider?
No, I claim I need only that this embedding, that this map is a homomorphism, where G is a joint representation, and here we have a joint action. And so such kind of embedding I'm talking about. Yes, and we have two embedding of such sort, and then no, in principle I can take as many embeddings than we have, and all elements which we get here commute. This is, again, this is some simple, a relatively simple exercise about semi-simple Lie algebras, and it is true in more generality, and maybe it will be also exercise for students. Right now I can formulate exercises, later it will be more complicated. But even here I explain not, I do not want to solve this immediately here, but I explain how to do it. Yes, and well, and from the maybe few words about the quantization of shifting of argument. So what? That I have a starting point of constructing my integrable system. That at least inside the universal enveloping now, if you believe that this is correct, we have many elements which commute. Yes, actually, the steps further will be the following, that such elements, from the point of view of shift of arguments, they are in correspondence of first derivative in this kt in t in 0. And as I said, this first derivative of central elements in Poisson picture give me precisely what is, after quantization, is going on to this. Then, if you are going on to second derivative, so what you do? You have K1, any central elements, and in principle you can take second derivative like this, and from the point of view of our integrable system, it will be next element from our integrable system. Anyway, if you take such, if you fix K and change A and consider the subspace in the space of function we generate by all these elements with respect to a joint action, you get actually the map from symmetric square of G into the space of functions on G star. And the element which we are talking about, here we have element A square, and it is going to next elements from our integrable system. The point is that, no, about this, no, quantization of this is also possible, but it is not so easy because we have many maps of such kind, and we need to choose some special ones to get the elements from our integrable system. Okay. Now, no, because later I will talk about screening and other things, I need to continue a little bit this business, to need the version of vertex operators in finite dimensional case. So what is this? It is simple things, and no, usual story is following, that we still play with the same semi-simple Lie algebra, and for such Lie algebra, we have Fermat representation with highest weight kappa. I call them V kappa. Yes, and no, vertex operators is some intertwiners, but right now I use a simple version of following, that suppose we have pi is finite dimensional representation of G. Yes, and my definition of vertex operator of type pi will be just map home to from pi to home C no, so it is standard definition. It means that if I take two Fermat representation in this finite dimensional case, then home from one to another gives us surely representation of G, and here I put G here, and it is a map from pi to home. No, symbolically I denote it by this way. Pi is living in a space of homomorphism from Vk1 to Vk2. So this is vertex operators, and in a fine case we determine vertex operator by more or less the same machinery. Then no, this is important, but well, and here pi in principle, no, finite dimensional representation is just because it is easier to work, and we will need only this now. But I do not claim that pi is irreducible. In principle, any representation, just embedding of such sort. And if you are talking about, if you have embedding to G, to universal enveloping of G, then by this way, no, because universal enveloping surely acting in any Vk, that by this way we get vertex operator of type G acting from Vk to Vk, like this. So any embedding of such sort give me the vertex operators acting from this to this, because universal enveloping is acting here, and so G is part of this, so we have it. Yes, and but in principle we have other vertex operator where chi can be different. Then, well, from the representation theory of simple fact from representation theory of semi-simple Lie algebra is following. Well, suppose you have Vk1 and Vk2, and suppose you have a finite dimensional representation pi, and I denote U the meaning of these symbols, but the question is how many of such vertex operators we have. Yes, and this is no, for in general this is not so easy, but we work with a simple case where chi2 is generic, I think. Maybe chi1 and chi2 are generic. Now, in this case, if you want to consider such map, like people from vertex operators, so they are saying that this is the same as a map from chi1 to y chi2 times pi. It is the same things. Homomorphism, what I'm talking about. Yes, and no, the problem appears if this tensor product is complicated. And surely if chi2 is not generic, that it can be complicated. But suppose that chi2 is generic. In this case, a situation is much simpler, and in this case, v chi2 times pi is isomorphic to direct sum of v chi2 plus nu, and here we have pi nu here. So what is written here? Pi is the sum of pi nu, and this is just weight decomposition. And if I take such product, the result will be the sum of Fermat representation and multiplicity of, Fermat representation which appear in this product have such highest weight, where nu is, as I said, and multiplicity is equal to this, the dimension of weight space here. Yes, and in principle, even more, that it is not complicated. It is easy to see that space of multiplicities can be canonically identified with corresponding weight space here. And in a moment, I will say how to do it. But if you believe me, then what? Then such kind of data just labeled by pi chi2 minus chi1. Yes, and maybe I confused pi with pi star, but I think so. But anyway, if you look to this, then suppose, for example, that chi1 equal to chi2. Then, in this case, we are interested in here chi1 and here also chi1 now. We are interested in pi 0. Pi 0, this is a weight subspace of weight 0, and then such kind of things which are rather simple. I just claim that what? If you have such map, then let us consider only weight space 0. And this weight space 0 gives each element of this has you a map from highest vector to highest. Therefore, if you have this, it means that you can distantly see some element from a dual space. How such things are acting here. And the statement, what I said, it is just statement that in the case of chi1 is generic, I think it is correct. Maybe chi2. I think chi1, but I hope I'm not confusing. Anyway, at least if both of them are generic, then it is definitely true. Then if you fix how 0 Fourier component are acting on the highest weight vector, then after that, or if you know this, you can construct all other matrix elements of our vertex operator. And the same story if chi1 and chi2 are not equal, then for example, in our case, what is this? Suppose P is just G, and still chi1 and chi1. Then a zero weight space here is just Cartan subalgebra. And we need to know how Cartan subalgebra is acting. So therefore, how it is acting, this is element from the dual space. And we have, no, for example, it means that we have as many vertex operator of such kind. The number is equal to rank of the algebra, the dimension of this. Yes, and by the way, it is in correspondence what I explained you when we're discussing the situation here. Here it is sure the classical story, but I have center. I can choose generator of centers. Number of generators of centers is equal to the rank. Then I can start to differentiate each generator of a center by all variables, and we have several copies of G, as many as rank. And no, because here we fix chi, it means center is acting by constant. So therefore, by this way, we construct all possible embeddings. Again, so the conception of vertex operator I have, now I need the conception of correlation function. In this case, what is correlation function? And well, maybe we do not need strongly this here, but maybe later we will need it. So suppose we have the following things, that I have Fermat representation y chi1, then I have Fermat representation y chi2, and then I have Fermat representation y chi3. Yes, suppose I have here pi, so pi embed pi1 embed to this, and pi2 embed to this. And if I have such things, I can do the following. I can take highest weight vector from this, yk1. It is highest weight vector from this Fermat representation. And then acting by p1, so we get something here. Let us denote it by this way. And after that, to the result, I can act by pi2. And so after that, this is symbolically mean what? That I have vectors here. They act by operator corresponding to some vector from this. It gives me something here. Then I act by some vector which corresponding to this. Then I go here. And then I can take my matrix element with y chi3. It is like this. No, this is knowing correlation function, because this construction in conformal business just give us this. But right now what we have, because here is some element maybe A from here, here some element B from here, then, and this is number. Therefore it is what? It is pi1 times pi2 to C. Such things are calling correlation function, and And we know, no, what we know? We know the weight, because we start from chi1 and go to chi2, and so this function non-trivial only on a part of the weight chi3 minus chi1. Okay, so definition of correlation function I have. Then, now what to do if you want to, no, now let us return to my problem. So I have G embedding to universal enveloping of G, and I take G second, which embedding to universal enveloping of G also. Yes, and now again, my problem was following. I have element A here, and I have element A here, the image or something, and then I want to say that the corresponding element, the image I commute. Suppose I forget about A. What does this statement mean? This statement means the following, that I have this embedding and this embedding. So therefore, I have two subspaces which are isomorphic to G inside universal enveloping, and I can consider two products, two directions. Let me write down it by this way, G1 times G2. So it means that if I take product of the images in this order, so it gives me map from this to universal enveloping of G. And we have product in the opposite direction. It is like this. It is going to universal enveloping also. Yes, in principle, there are two different spaces, but here we have a symmetric power of G as a part, and here I also have symmetric power of G in a part. Yes, and then inside universal enveloping, I have skew symmetric power and symmetric power, skew symmetric power and symmetric power. Skew symmetric power we do not interest in at all, but the statement is that this skew symmetric power here coincides with this skew symmetric power here. And this is the same, no, well, this is why, because this is just what is saying here, because we have element A1 times product A2, and product A2 times product A1. I want to say that these two elements are the same for any A. And if it is true that actually this is the same story, that this S2 and this S2 are the same. Yes, and actually this is what we have to prove. If you want to prove that such kind of elements commute, then you have to prove this. And surely it is good not to use correlation function and just try to prove it directly without considering representation, Verma things, and so on. But for us, it is more convenient to use it, because what? So you have G1 times G2, and you have G2 times G1 here, and it means that you have two embeddings, maps at least, S2G to universal enveloping of G, and we have S2G to universal enveloping of G. Yes, which one of them constructing from this and second constructing from this. And we want to prove that such kind of things are the same. And because we have map from this to this, we can consider the Verma representation, V kappa. Kappa will be generic. And then we have a picture like this. No, S2G is not irreducible, surely. But at least we know from the generic arguments that each of such maps characterizes by we have to take 0 Fourier component and consider the corresponding element from here. So any vertex operator of such kind for generic chi is determined by the way how 0 weight component is acting on the highest weight vector. Then, but this is nothing as the symmetrization of correlation function, because I act first by this and this or opposite, and this 0 part which determine what is going on is just this correlation function. So if you, like many people, like me, like this word correlation function, so what does it mean? That we have these two things, and we need to prove that symmetric part of correlation function the same in this order and in this order. Yes, and this is what we want to prove. And now, if we want to prove it, we need to know something about correlation functions. What? No, now they are just some matrix element, but no, the people who know how to derive the equation of Knyzhnik-Zamolodchikov, they know that again. So for Knyzhnik-Zamolodchikov, the story is just the same, but difference is that group is G hat, and vertex operator depending in Z. It is evaluation representation of Kac-Moody, but we interested in matrix element of the product, and people are saying that such matrix element in affine case, this is function in two variables, matrix value, satisfy Knyzhnik-Zamolodchikov. And here, as I promise you, this is a baby version of Knyzhnik-Zamolodchikov. And for that, we need the following. If we have embedding of G to universal enveloping of G, then, and if this G is acting in Fermat representation, then surely this image here commute with quadratic Casimir. And we just, if we have embedding G to this, and suppose E gamma just basis to with inside gamma roots, and E gamma is the basis in G, and Casimir is E gamma, E minus gamma plus E minus gamma, E gamma, and plus something from 0 part. And I can take this element and suppose the G is acting here. So it is embedding, so, and I can fix some element A here and consider A1. A1 is the element acting from M chi to M chi. Yes, and because it is quadratic Casimir, then this bracket is 0. But if it is 0, it means that we have some algebraic relation. And this algebraic relation is looking like what? We have something from here. Yes, but from here we have evident things. It is E gamma, and here we have E minus gamma A1 plus this bracket. No, it is this bracket, then this bracket. Then we have E gamma A1, and here we have E minus gamma plus some additional term. And altogether, it gives us some algebraic. So it means what? It means that in our Fermat representation, we have, no, because of this, we have the action of G from here, and we also have G trivial. It is also some embedding, and this embedding just this. And we have the algebraic relation between this and this. And this algebraic relation is this one. And what we need to get Knižnik-Zamolodchikov equation, this is precisely the same in a little bit more complicated situation. Now, how to use it? In Knižnik-Zamolodchikov case, you write down something like this, considering correlation function, and it satisfies some differential equation. It means if you do not want to formulate it in terms of differential equation, it is some recurrent relation to a coefficient of correlation functions. Therefore, what we have to do, we have to consider two correlation functions which we're interested in, then look what property to this correlation function follows from this, and then just see from this property that this correlation function are just coincide. Again, we need symmetric part, and for symmetric part, we are, no, and as I said, that, no, as exercise, this is some program of action. So you have to write down what follows from this, then to write down the property of correlation functions, which you can see from that, and after that to see that what? That you have two embeddings, first, maybe, and second. And part of correlation function is how symmetric power of Cartan is acting on highest weight vector. No, correlation function is I act, and Cartan part here is also acting, surely. And action of Cartan here and action of Cartan here is definitely coincide. It is no doubt symmetric parts. And after that, you're using this Knižnik-Zamolodchikov type equation, and then just prove that corresponding elements are commute. Anyway, how conceptual is proof, and is this proof is the simplest possible? I am not completely sure, but conceptual in some sense. Yes. One comment. Then, if you are talking about Casimir and such kind of equation, it is possible, it is easily possible to write down without using coordinates. And this is the following. So suppose you have G I'll explain what I write in a moment, but now I want to write the following diagram. First of all, G isomorphic to G star. Then we have co-bracket map from G to lambda to G. Then I can go from this to lambda to G times G. Yes, and this is going to G times G times G. No, this is part of here, and this is going to G now I only want to say that vertex operator G inside endomorphisms of MK. It is satisfies the following condition. So let G be so what I want to do, I take element A from here and element B from here. And suppose this element A is A1, and here it is A trivial. Then I go by this, I take A, but it will be later. But first I take A and B, then I go here, and then I go here. Yes, and now what is this? Here it is element from S2G, and this S2G, I want to send it to an endomorphism of MK, and this map is what? If I have some x here and y here, and this belongs to symmetric power, then it is go to xy plus yx. So what I want to say that I have some embedding G, and I write down this as some algebraic property. So G from here times G from here, and then I'm going and so this is operator, this is operator. By this way, I produce some operator from endomorphism MK, and this has to be 0. No, I claim that this is just some. No, this is just the same things as to formulate what I said here in coordinate way. And if you try, you can easily do it. In words, it means that G trivial and G any others, G1, connected by some algebraic relation, and by this algebraic relation, we can prove that our elements are commute. Now, yes, maybe now I skip here some details, or maybe say it a little bit later. But what we have now? We have G. We have G also. It is a joint representation. And also we have a vertex operator which is corresponding to this G. And vertex operator in principle acting from m chi to m chi plus gamma. Gamma is weight space from here. So vertex operator, according to what I tried to explain, they can act by this way. And because in the same simple case which we are talking, multiplicity of all roots is 1 and only multiplicity of 0 part is bigger, therefore if gamma is if gamma is not 0, then we have up to a constant 1 such map, and if gamma is 0, we have many. Suppose we have A belongs to G. Then this element A, which is acting from m chi to m chi plus gamma, I want to call screening. And yes, and no, and how this can compare with what we know from screenings. Now I fix the element A, and it means that I can construct some operators which can act from m chi to itself, or can act from m chi to m chi plus gamma. Yes, and all integral of motions, no, they are, no, at least if this operator acting from m chi to itself, this is a part of our integrable system. And then commutative algebra, what we are talking about, can be determined actually as algebra which commuting with these screening operators. Yes. And I think I'll explain this in a little bit more details. So because now I want to go to screening operators in more generic case. But let us because I do not finish the description even in finite dimensional case, but better to return to this later. And maybe I want to say that this finite dimensional version of screening business, I do not know place where it is written. Maybe nowhere. And no, we discussed maybe some years ago, or maybe almost 10, this with Leonid Rybnikov, and he has some notes about this, very incomplete, and this is only the place where it is written. But I think without such things it's rather complicated to understand what is going on in general. But now, well, now shifting of argument and it is generalization and KDV type systems.
Maybe we can take a break.
Why not? We can. 5 minutes, 10 minutes.
10 minutes.
No, it's fine. Okay. Maybe about this I forget to say one simple thing which clarify the situation a little bit. And suppose our G is just GLN. And in this case, if we take universal enveloping of GLN, and I'm talking about these simplest things, about embedding G to this. And in this special case, we know very explicit formula for this. This is because we have trivial, which Eij goes just to Ij here. So it means that this is embedding trivial to linear part. But we can take a little bit more complicated, going to quadratic part. So such kind of things give me quadratic operators here, and this is more or less evidently example of what I'm talking about. And in principle, you can do more. You can write down Eijs here, and it will be Ei alpha 1, E alpha 1, alpha 2, E how S minus 1, maybe J, something like this, summation by all alphas, Eij fixed. Then it also gives us the embedding. And no, this is quantum formula, and classical formula is looking very similarly. Yes, and then from this point of view, if you do not want to use this correlation function business, you can just check directly. So it means that for any S, you write down Ij, Es, Ij. And you get a collection of operators labeled by S. And the statement which we are talking about, they just compute. And about this, I want to say that it is not, no, it is follows from maybe some Yangian business and other things. But if you want to do it just directly, just commute such two things, it is also possible. Write down some blah, 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 blah. In the end, they will be equal. Yes. Then and screening in my language is just these things, but let me say a little bit more about this. So, well, first of all, shift of argument is shift of argument, but I want to use this shift of argument in the following situation. Suppose my Lie algebra is not G now, but G hat. It is G times C. Maybe I can write down it by this way, plus central element. Or I can, considering C infinity, again it will be function on a circle plus central element K times C. Yes, and it will be just generalization in the sense that we get dependence in Z here, and on new things is dependence central extension here. We have not this. Yes, and again, just recall that surely everybody knows that cocycle Fj, two elements from here. sent to residue of dfg. So these are two elements from here. df is one form, g is function, product is one form, but we calculate their pairing in G, and the result is residue. Residue is here, and here we just take integral by S1 if we are talking about these things. Anyway, this is G hat. Now, what is dual things? G hat dual, this is Poisson manifold. Yes, and this Poisson manifold is what? It is the following usual story that these dual things can be identified with the following data, D plus A. And this is just connection on a circle, or in a punctured disk, as you like, but we prefer to have some. Without this, it is just connection. So, as usual, this is operator which is acting from 0 form on a circle times G to 1 form on a circle times G. Yes, and we consider all operators from this to this which have such form, and this is just D, and this thing is element. No, because I want action from this to this, so it means that as in this connection language, it is element from here. Yes, and then what? This operator itself, it corresponds Poisson structure. Why? Because let us fix beta, and later we do not want, but let us fix beta. It will be symplectic leaf in my manifold, and it is usual story what we consider. Then our infinite dimensional manifold is this, and tangent space D plus A plus variation of A. Variation of A is the element from here. So, so this is tangent space in a point A. And this space is dual to this because of, I can take product, calculate here the quadratic form, and then integral. So it means this is tangent space. And this is cotangent space. Therefore, what we actually have, the statement is following, that we have Kac-Moody this algebra. And according to standard story, we can consider dual space. And we expect, because it is Lie algebra, expect to have Kirillov-Kostner structure here. And what is this? Space is this. And about duality, duality is what? Duality is going by which way? This dual to this, and this dual to this. It means we just organize it by this way. And if you look to this operator, and in principle you can forget about this and just consider the space of all such operators, and it means that we have space of operators. Tangent space is this, cotangent space is this. And this object is operator acting from cotangent space to tangent space. And this is what in Poisson geometry is calling the Hamiltonian operator. Because you have manifold, you have point, you have tangent, cotangent space, and operator acting from this to tangent space. And this operator has to be skew-symmetric. And then if we naively send it there, it gives us element from this. And this is Poisson structure. Okay. So it is nice and highly used. Yes, again, in principle, we need parameter beta here, but I prefer to forget about it, like people usually do. Yes, then what we did in the case of finite dimensional algebra, we consider G hat and look to invariant center of a corresponding Poisson structure. Function which commute with all other functions. And here we can find them, but at least formally we can, because what we need, this is the space and the group. Our group, actually, Lie algebra, corresponding group, is acting on such objects by gauge transformations. Therefore, invariant functions are functions which commute with this stable with respect to this gauge action. And so invariant function, what we can take? We can consider this as connection on the circle, and then we can calculate the monodromy. Maybe monodromy matrix. What is the best notation of this operator? D plus E. And no, monodromy matrix itself surely depends on the choice of a point, but if we take trace of monodromy matrix, then it gives us the invariant functions, and monodromy matrix itself is the element of corresponding group G. So in principle, we can take any character, any invariant function on G, for example, character of a reducible representation. And we can take character of this, and then by such things we get function or at least formally. If we work in the case of punched disk, this is the problem what we are doing. But if it's really living on a circle, it's okay. Yes. Then no, and it is something. And at least this shifting of argument things can be used in this case. And for example, what we can do. Suppose that G is equal SL2, and in general also, and we can take trace in this case of this monodromy matrix of D plus E, but we have also T times some A0. Yes, and no, in principle, we can shift by something where we have D, but let us not do it. It is simpler. Therefore, we get some functions depending on the space of connection, depending on T, and at least if they are well defined, that formal calculation says us that they commute with respect to the structure. And this scattering program, which exists for 40 years, it has many problems. One problem of this commute of such kind of functions. So again, the problem is completely the same as finite dimensional case, only the problem that it is much more complicated things and more ill-defined. But at least we want to find, in this case, we go to universal enveloping of G hat, for example, SL hat. Let us put parameter k here. So it means situation, as I said, for Virasoro and so on, this quantization procedure working by the same way. If you go to standard definition of fine-cut-smooth algebra, it will be algebra or something, the vertex operator algebra depending in k. And if k go to infinity, then you go to quasi-classical things. And the problem is to find out the commuting operators which are acting here. And so how to do it? One thing is that we can try to repeat these finite dimensional things that, but so how? I can take this d plus a plus t a0, then taking this monodromy, and I can consider d over dt t equals 0. Yes, and then what did he give us? No, because by monodromy, so better to put trace of monodromy here, or at least I have it in mind. Yes, and therefore, again, if to take this naively, it means that on space of connection d plus a, you have functions depending in a0. And so it is more or less mean that you have a map from G times a function on a circle to the space of functions on our D plus A space. Yes, and no, it is the same story, but in finite dimensional case, we had map from G to universal enveloping of G. Yes, and now by such way, no, first of all, we are still living in a quasi-classical limit if we do it, so it means k go to infinity. Yes, and so it is G hat here, and here it is G times C as one now, but it is the same things, and so it is possible to think by this way. Yes, and no, and the strategy which I discussed before the break, that we have to take some element from this and but so, but the next question, this all is fine, but I want embedding to universal enveloping, not in quasi-classical things. And but maybe let me say what people usually doing with these monodromy things, that before any quantization, they consider the expansion of this monodromy matrix around t equals 0. First derivative, second derivative, and so on. And it gives me us collection of functions, and depending on A0 here. And this collection of functions are commute with respect to a Poisson structure. Yes, and after that, the people like Fadeev and the later Molochikov and all people who are did with this, they consider the expansion of this in t equal infinity. It is much more subtle and less algebraic at all. You know, even this is strange to call too much algebraic, but they consider the expansion of this to t equal infinity. And to be more precisely, maybe later I say more, maybe not, but it is possible to take this, take logarithm of this monodromy and expand it, result in t, and the corresponding elements are also elements from our commutative algebras. And standard notations are expansion in t equals 0. They are calling non-local integral of motion. And expansion in infinity, they're calling local, and they are local integral of motions because of some mysterious reason. That let us discuss them separately, and let us consider a little bit what to do if t equal to infinity in this language. If you want to make up quantization, it's nobody knows. But at least if you are going to say something about t equals 0, so well, no, we can use this vertex operator point of view. So it means what? That we still consider SL2 head case. It is does not important, but suppose, and k level is equal, fixed, suppose, and we have Fermat representation chi1 and y chi2. Yes, and before we had G, now we have these things. So we want to have vertex operator, which is SL2 times. Now, in this case, if we want, we can even write down this algebraically by this way. It is possible. So, no, especially if chi1 not equal chi2, it will be a problem. But suppose they are equal for a moment, then it means that we just have embedding of these two operators acting from this to this. Now, first of all, no, if you are talking about vertex operator, then the situation with them is completely the same. So what does it mean? It means that we can formulate it even in general case. Suppose it is G times C the inverse, and what is going on here? So this is Verma representation. Verma representation on a top level, this is just representation of G. And this is just Verma representation. It is G times 1 is acting on the highest weight vector, and 1/2 of it kill. Cartan from here give us highest weight, and all other things give us this. And the whole story is this. Then we have this times G T inverse and so on, and then we want to have a map of such kind acting here. If we want to determine it using more or less the same arguments, and all people who are working with vertex operator, they are doing this. Now, if we have this, then first of all, G times 1 have to act. G times 1 from here have to act from this to this. But this G times 1 acting on this space, and no, because we choose a representation of such sort, here we have Cartan times 1, and it is acting on this vector by this way. And so the statement is that if we fix how this Cartan acting here, after that, we on the top level, we are doing the same what I did before. But after that, I want to repeat this story there, and then we see that vertex operators of type G, acting from representation to itself, according my notation, are labeled by usual Cartan, in this case, from finite dimensional, and it is how it is acting on the highest weight vector. So element from this space determine the vertex operator. So this is the first thing. Now, second story was following that. No, again, in this space, G times C Z inverse, I can choose some element A. And no, because collection of vertex operators are labeled by element from this, I have set of operators acting on Verma representation as many as dimension of this. Yes. And such kind of story pretend to be the quantization of this monodromy and blah, blah, blah. But no, even in finite dimensional case, suppose we even know what is going on in this classical story, in this Poisson business. No, we have, but we cannot use it. At least it is not clear how. It is just a problem. You have a family of such operators, and the fact that they are commute. And it is possible to prove, maybe by several ways. One way, use the same machinery with correlation functions, and so on. And yes, and so, no, practically, the fact which we have to check here is also the same as finite dimensional case. Only problem that situation is infinite dimensional and so on. So it means that I have one vertex operator, maybe GS1, 1. 1, it means I choose some vector from here and consider the product of 2 and in the opposite direction. And again, the statement is that symmetric powers in both order have to coincide. If yes, then it is actually what we want. Yes, and how the proof is going on, that at least we no, if you know about Knyzhnik-Zamolodchikov business, then it is going along this way. So how we can imagine this story? One vertex operator is in G first, it is depending in Z1. And then it is G second, depending in Z2. Yes, and we consider acting this on highest weight vector, in this case chi, and take scalar product of this. Yes, and correlation function is this. So it is function in two variables, Z1 and Z2. No, with value in G times G or G star times G star, this is as you like. Yes, and the fact that such kind of elements commute, this is some fact about these two correlation functions in two different orders. And so again, what you have to do, you have to write down this Knyzhnik-Zamolodchikov equation to this function in two variables. Actually, it will be trigonometric maybe in this case, but not completely sure. No, because something we have in 0 and in infinity, it is something like this. Now, maybe, no, in this case it is yes, but let me say at least formally, what to do. No, before I said that, well, we have this key and I shift it and consider the first derivative in t. Yes, but if I consider second derivative of t, so what it will be? But how to see it? First things, let us calculate a little bit the following, that what is the, no, I explained that we have operator D plus E, yes, and I put here T times A0, and then take trace or some other, no, suppose for SL2, trace of monodromy of this, and consider derivative in t equals 0. So what is this? I said, I more or less explained the answer, but operator is acting from 0 form times g to this operator and all these operators surely is acting from 1 form times g. And if you consider the first derivative, then it is possible to write by the following way. You have to take this d plus a, then d plus a is is operator acting from this to this. Then you have to take solution S, and then times a0, and then taking integral. No, this is more or less the same what I said, but a little bit different language. And no, and the question is a0 here is suppose it is the object belong to Cartan, for example. And if we want to take some such kind of integral, we do not like multivalued solution. We want a solution without monodromy, and if we take it, such kind of integral, it really gives us quasi-classical things of what I did. And such kind of differential equation, it has solutions which are which have not monodromy around. Yes, and yes, and it is some kind of formula, and if you look to a theory of differential of any book about differential equation, even in a case when it is not matrix valued, but suppose A belongs to L.1, you write this, and in this case monodromy is simple, surely, and you expand this trace. No, it is not trace, it has to take maybe monodromy itself. I do not know, in 0. No, I cannot say it correctly, but I want to say that in the textbook this is the following, that if you take expansion in t, and if you take second coefficient, second derivatives, then it will be the integral of such sort as x1, I think as x2, a0 x1, a0 x2, but you have to take the integral properly. At least it has to have meaning. Yes. Now it is only idea that if you write down expansion, that first expansion it will be one-fold integral, second expansion it will be two-fold integral, and so on. And yes, from the point of view of vertex operators, This idea can be formulated by the following. Well, you have a Fermat representation, Vk. You have the action of C2 G, for example, tensor C, Z, Z inverse from Vk to Vk. Yes, and as I said, we have a collection of vertex operators, and first element of our commutative system is the image of A here. Now, the question is how to write down other elements. And other elements are the following, that we have a collection of vertex operators. Vertex operators can act from Vk to Vk plus gamma, like in finite dimensional case. Yes, and if you want to construct so non-local integral of motion of second type, it will be some combination. Vertex operator this, vertex operator this, vertex operator this, vertex operator this, and quadratic combination here. And such kind of combination give us the second element. Third element are constructing similarly, and so on. And so one of my goal is to explain how these things, how they are going. Yes, but well, no, to explain better how to construct quadratic operators, I need to explain better what is going on in finite dimensional case. Maybe I do it in the beginning of tomorrow. Now I want to say two things. One thing is that if you consider Virasoro, what to do? Now, in this case, situation is following, that you take differential operator d squared plus q. And I explained to you that this is our story. And if you want to construct KdV, you take such differential operator on a circle, you add here t times q, some q0, and then taking monodromy, taking trace, and it gives you some operators which are acting, no, it's some Hamiltonians. And again, we have here second Hamiltonian structure, we expand it in T, and we have some rather complicated functions, very non-local, on connections on d squared plus q, and they will be the counterpart of this shifting of argument methods here. No, you can ask me, no, from Virasoro point of view, all these quasi-classical things can be understood as a sort of hint, maybe it is hard to use for quantization, at least directly. But the result will be the following, that suppose we have Virasoro representation. We have some C and we have some H. And we have Fermat representation depending, say, in H and C. Yes, and we know to construct something which is acting from this to this. Again, in the case of G hat, we cannot, no, we just follow finite dimensional case, and we did it there. So we took a joint representation, and I consider this a joint representation as a part of some extended algebra, and so it gives me first operator in this case. Yes, and in Virasoro case, we can do it by two ways. And one way, trying to study operators d squared plus q and just understand what actually we need. The formation in this case cannot be very simple. Other way is following, that we can take Virasoro and we can take SL2 hat and take Fermat representation of this some h prime k here. And we know, as I explained, in this case, for constructing of such operators, we used a joint representation SL2 times C ZZ inverse acting here. After, if I want to go to Virasoro, I can use quantum Dirichlet-Sokolov reduction. And what is happening after that? We have this and such kind of vertex operator is acting here. Then I can make up the quantum Dirichlet-Sokolov reduction, and what is happening? After that, it gives us Fermat for Virasoro, and the corresponding vertex operator after reduction give me what is calling in Virasoro language the field phi1,3z. And this is actually what has to be done in Virasoro case. So if you remember Virasoro case, then in Virasoro case we have the following story. We have Fermat representation, VHC, and we have the action of operators of phi, say, 1, 2, for example. Operator phi 1, 2 can act h plus something or h minus something c. And operator phi 1, 3 can act from this to this minus plus, and it is not important, but phi 1, 3 can act from this to this. Yes, and this is actually the story in Virasoro case. So we take field phi1,3z. In Virasoro case, it can be operators which is acting here. We take 0 Fourier component. This is some operator acting from this to this, and it gives us at least one element from our integrable system. And after that, the problem is again, and all what I am talking now can be understood as a guessing work. So I'm just trying to find correct vertex operators which give me integral of motions. But for example, this choice is correct. So it means that this is a part of big integrable system which commute integrable system which commute with this. Now today, in this Virasora and the SL2 head cases, I explain only the question that, okay, right now we have only one operator. And for SL2, no, for SL2 head, for SL2 head, for example, we have one operator for G hat. We have, if we take Fermat representation, then I have vertex operators G times C, the inverse acting here, yes, and to be precisely what is, let us make some choice that I have such kind of vertex operators, yes, and here we have G times 1, here we have Cartan, and suppose chi will be how belong, maybe not chi, maybe mu, belong to H star, how Cartan is acting on a highest weight vector. Yes, and also if I want my integrable system, I have to choose some element was A. This A in principle is here. But suppose I want, and choice of A is in my hands, I can choose any. But suppose I want to diagonalize it, and so simplest choice is following. Suppose in G times C, the inverse, again we have G, and again we have Cartan here, and in Cartan we have some element mu. Therefore, mu is the element from here, and mu is A. It has to be fixed. Yes, and in this case, mu in my notation labeled vertex operators. So I have many operators, as many as I have nu, but mu is fixed. And because mu is chosen by this way, and it is graded space, it has bigrading, and this is homogeneous with respect to energy grading and with H grading. So it gives me some operator acting on this space which preserve the homogeneous components. And after that, I have a problem of diagonalization. Now, as I said, this operator, they are screenings. Now I have the following problem. I want to find out local integral of motions which commute with this operator. And so what does it mean? It means that now I'm talking about the following story, that I have G hat. I have vacuum representation of this G hat. And in vacuum representation of G hat, I can choose some operator, element O, and create the corresponding field, OZ, and I want this. I want to find all O such the corresponding operator commute with such operator which I construct. Yes, and I want to say that in this case, for example, how this is related with this business with shifting of arguments, I can say something, but I do not want. We now understand it is a completely separate problem. I want just to find how many and just to describe all these operators. And for example, in this case, answer will be the following, that first of all, I choose it very explicit, and in this case, with my operator, Cartan times C, the inverse commute. So it is an interesting part of what is commuting. And then I can go to cassette things and ask who is commuting there. And then I can find that I will find operators, they are living on the levels. One level, such operators, vacuum representation is graded. So such O has element of grading 1, grading 2, grading 3, and so on. And in this case, we can find one element in each level which commute with this. Yes, so now I want to stop about this business. Maybe I formulated what I want. Now I want to change, not change the subject, it will be the same, but I go to free field realizations. Screenings and quantum groups. So I have 15 minutes, but I want to start. And right now you can forget all what I said till this moment. And later, tomorrow, it will be clear why I am talking about the same things. Okay. Let me start. Algebraic, pure, no vertex operator algebra, nothing, algebraic counterpart. No, I promise you that screenings here and screenings here, I construct some bridge, but now my construction will be the following. First, let us live on a lattice. Simplest case is the following. I have the following algebra. This algebra lattice is one-dimensional lattice now. In each point I have element xi, and xi xj equals some q xj xi. Yes, and if I is less than j, and q is some parameter from C star. So this lattice can be finite or not, but I want to find here, I consider algebra generated by all xi. Maybe even later, maybe more, but xi inverse also. Okay. Yes, and screening S. In this case, it will be the sum of xi. Yes, it is, well, how to think about this? This algebra is right now finite sums of these x and their products, yes, but this thing is in principle infinite, from minus infinity to plus infinity. And now let me do the following, and it will be important later. Otherwise, S later will be the element of a quantum group. But this is later. Right now, I want to write down the action, the joint action of S. Maybe it stopped or not. I don't, the joint action of S on this algebra. What it is doing? I take, no, the, let us say the following. Algebra generated by this xi is graded, and now I need only very simple grading where degree of xi equal 1. Yes, and In this algebra, if I take element A of degree I of degree S and element B of degree T, then I define the Q bracket AB Q as AB minus QST BA. Or minus. I want this be that xi q bracket xj is 0 if I is less than j. Is it correct or opposite? No, I think correct. Anyway, so this operation is just q bracket, and no, this is natural analog of usual bracket, and if I take my algebra and take some element from there, for example, no, any element, but maybe finite right now, then add S. If I apply it to some element B, no, by definition it will be in some direction. It will be, maybe it will be Q bracket, like this. This is just the definition of the action. No, it's the definition of this operator. Now, now let us look what this operator is doing. If we apply it to just xi, we have xi here. Then this xi, q commute with all elements here, and not q commute with all elements here, if I also not mixed left and right. At least it means that if I take q bracket of this, then to this xi, so what it will be? It will be xi, maybe square, maybe it is, but xi square plus xi times with some coefficient tail which is going on here. So because it is what? It is, I take such q bracket, and so what is this? It will be xi square times maybe 1 minus q, yes? And plus xi times the sum of xj if j is less than I. It gives us this, and here will be some coefficient also. Maybe the same. No, the same. Because xi, xj, I think the same, yes. So naively it means the following, that we have something sitting in a point I, and then I take this xi and act by this adjoint action, and so it gives me the xi maybe times some tail. Now, if I do not like tail, for example, then tail does not appear if I take something of degree 0. If I take xi plus 1 inverse, for example. Then if I take the object like this and start to calculate Q bracket with this, that it gives us something, but it will not be here and it will not be there. Because this object itself, it has degree 0. Therefore, it will be 0 from to the left and 0 to the right. Yes, but and it means the following story, that my operator add s is acting what it is doing. So I have big space which I consider there. And here in this space I have a part which has degree 0 in axis. Yes, and suppose it is my algebra maybe A, for example. It is 0 part of this, and this add S, send this to A1, because it does not create these tails at all. Yes, and no, after that, no, surely I can apply my S again, but in this case, some tails surely appear, and maybe it is not bad, but at least this operator acting from this to this. And why this algebraic, simple algebraic things, how much it is related with what we are doing? So, well, in degree 0, these are 0. What kind of elements we have? No, we have some elements xi plus 1 inverse, and such products actually generate the part of degree 0 in my algebra. Yes, and if I denote this by sigma I, then now our commutation relation become local in terms of this sigma. Sigma I, sigma j, they are commute if they far. If but sigma I and sigma I plus 1 not. It is some relation between them. Yes, and what is going on? Algebra A0, this is 0 part of our things. This imitate vacuum representation of some W-algebra in principle, because it is not in some vertex operator algebra. But right now it is just algebra. Yes, and we can take actually this is the imitation of vacuum representation of free vertex operator algebra, but it does not matter. That I want to say now only the following. In A0, we can take the subalgebra which stable with respect to this, so, which consists in some elements which will be a combination of these sigmas, P, say sigma, maybe sigma I plus 1, such that the add S which I apply to this P is 0. Yes, and this is some way to factor out from big algebra to small algebra. Yes, And this, no, this is why I'm saying about this, because in all story which I started with, what was it? Integral of motions, yes, but logically is what? That we have some vertex operator algebra, which is something. And then I have some operator which I constructed. It was what was written here. It was some integral of some vertex operators and things like that. And I'm interested in a part here which commute with him. Yes. And I wanted to say that it surely looks much, much more complicated than what is going on here. But actually, algebraically, no, this example, if we are talking about it, it's more complicated, but similar nevertheless. It is simpler. Yes, and no, subalgebra in A0, which commute in this sense, which commute with this S, or which is stable with respect to this adjoint action. This is some counterpart of Virasoro. So inside algebra generated by this sigma, we have some subalgebra. And this subalgebra is how it is going. That we have A0 and operator this add S acting to A1. And this is vacuum representation of Heisenberg. This is representation of the same Heisenberg but with different highest weight, and this is intertwiner operator. Or you can think about this in this language. We have some Virasoro here, the subalgebra here. And this object, surely because it is A1 is the representation of A0, and surely this is representation of subalgebra also. Therefore, such kind of operator give me the intertwiner between representations of two algebras. Yes. And no, to compare it with the real Virasoro, it is also possible, but at least even this, it is some interesting game, because no, I forget formula because I think it is not very much important now, but it is some expression, I think, in sigma I plus 1, some function in them which commute, no, not with this, yes, with sigma. Who is Virasoro, or who are the generators? There are some combination of sigmas. And we, in principle, we can try to find them. We have a joint action, and we look, we need, in principle, a local expression, I mean, which is finite. But first, which we can try three things, x1, x2, x3, and find out just here what kind of combination commute with my screening. Yes, and it gives, if I remember correctly, it gives me some generator. Yes, and therefore we have, no, I can confuse, maybe we need 4, but I think 3. And we have some kind of things here, 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 here. There's some combination, and then they generate some algebra which is the analog of Virasoro here. Yes, maybe now it is time to stop, but no, this case is so good that it is reasonable to write down this explicitly because, well, we have some function in f sigma 1 and sigma 2, and then I take the bracket with s, and I want this be 0. And if I remember correctly, it has some difference equation to sigma 1 and sigma 2. Then you can solve it. It will not be polynomial, but doesn't matter. Right now, we do not worry, it will be something. And they generate some kind of Virasoro. Yes, and then we will look how this machinery is working. That, for example, simple calculation, which I only can mention now, well, so suppose you have any place, A1, for example, and you start to add s, then add s, and so on. Suppose you are doing this many times. Now, in principle, if you are doing 2 times, 3 times, 4 times, the expression will become more and more complicated, but structurally will be the same. It will be something local times many tails which are going on in some direction. No, it's okay, but suppose that q power n equal 1. Then, in this case, it is happening what is usually happening with quantum group in the root of unity. It means that if you make up such things n times, then all these tails canceling, and you get, again, local expression. Yes, and no, this kind of machinery actually very close to what real screening are doing. And we have to talk a little bit about this algebra. This algebra is maybe standard part of initial quantum group courses, but it's good to formulate precisely what is going on. Because, again, the last things, screenings or brackets with something, they will be also analog of this. But in vertex operator algebra, it can take vacuum representation of vertex operator algebra and send it somewhere. And this is precisely what is going on here. This is like vacuum representation, and this is some other representation. And later we need some what my plan to do? I want to explain how the machinery of local and non-local integral of motion are working here, then return maybe to the simplest case for usual vertex operator algebra, and then explain, if it's possible, how it is working in our little bit more complicated case with this shift of arguments. Business, because there's the same situation, but confusingly hidden. Then, okay.